Okay. Now, so far in this extremal graph theory, we talked about Ramsey theorem and its generalizations. Right? And these theorems talk about the subgraph relations. So in the remaining of this chapter, we will talk about other containment relations. Okay, so oops. Today is lecture 22. So minors. So extremal graph theory with minors, right? So the question is simple. What is the maximum number of edges in an m vertex simple graph G without KR minor? How many edges can you have if you don't have a complete graph on R vertices as a minor? Right. So we can start from easy case, right? So no K1 minor. Okay, nothing. As soon as you have a vertex, you will have K1 minor. No K2 minor. So G has no K1 minor, then you have no bound at all. If you have no K2 minor, the number of edges is at most 0. Trivial. How about no K3 minor? So graph has K3 minor if and only if, so simple graph has K3 minor if and only if it has a cycle, right? So if you don't have a K3 minor, then it's a forest, and forest has at most n-1 edges, right? So number of vertices of G is n. How about K4? If you don't have a K4 minor, what do you get? And that's where we have something called, so this is trivial, and this is something called the series parallel graphs, which are graphs you can obtain by series composition and parallel composition. So what I mean is, here are operations. You can add an isolated vertex, you can add you can subdivide an edge, you can add a single edge, you can subdivide it, or you can duplicate, make a parallel edges. So these are the operations. Adding some isolated edge. So you start with some collection of edges and isolated vertices and do these operations. And it's known that graphs without K4 minors are exactly those graphs that can be built by these two operations. And these graphs always have a vertex of degree 2 if it's simple. So that allows you to prove this quite easily. I'm not gonna tell you how, but oh wait, did I say correctly? Yeah, those graphs always have vertex of degree 2, so that means number of edges is gonna be at most twice. And then by induction you can prove this, right? how do I know that these graphs have always vertex of degree 2? That's because if just look at the last operation. If it's a parallel composition, then it's not a simple graph. So the last operation is always the subdivision. So when you subdivide an edge, then you must have a vertex of degree 2. Okay. But another way of proving it is okay. Let's see. Right, this is actually easy exercise, right? Assume the graph has certain connectivity. Let's say 3 connected, because if it's not 3 connected, you can apply induction. Just split it into 2 pieces and get the bound on the left, bound on the right, and then combine them. And once you have a 3 connected, then you must have K4 minor. So, right. All right. So I'm not showing you the proof, but this is again easy. From now on, it's slightly harder, but still manageable. So no K5 minor. And it was due to Wagner, who characterized graphs without K5 minor. And it's almost, I mean, it contains all planar graphs and a little bit more. And from there, one can prove the number of edges is at most 3n minus 6. No K6 minor. So Wagner actually has a structure. So we have full description of graphs without K5 minor. We don't have a full description of graphs without K6 minor, but what we do have is this bound. This is due to mother. Now the proof gets a bit harder. And then no K7 minor. Again, mother proved the tight theorem. So so far everything is tight. Tight means that you have an example which achieves the equality. So let's see the pattern. Okay, so so no KT minor. So what's the pattern? Okay, so the coefficients of n is like t minus 2. And when you look at these numbers, like 1, 3, 6, 10. So you add 2, 3, 4, 5. This is somewhat familiar, right? It's some of the integers. So what's the guess? Right. I'm adding 1 up to t minus 1 up to t minus 2. Right? So is it gonna be something like this? Maybe. And this is true for t at least 7. Okay. And surprisingly, this is not true for t is 8. What's gonna happen if t is 8? Well, 8 is like 6n minus 8. So 6 times 7, 37. This is what we want. Now let's look at the graph called K22222. What that means is multipartite graphs with 5 backs, and between different backs Oh, so this is same as in our notation, this is same as that. All right. Now, so this is a 10 vertex graph. And number of edges is 10 choose to minus 5. Okay, 10 vertices and 5 choose to minus 5. No, 10 choose to minus 5 edges, which is 45 minus 4, 5. So 40 edges. Right. What is the bound? Like 6n minus 21. So if I put n to be 10, then that's 60 minus 21. Now that gives me 39. But this graph has more than 39 edges. So if what we expect is true, then this graph must have k8 minor. Now I will argue that this graph cannot have k8 minor. Why? Why it doesn't have k8 minor? Right. Suppose that I have a k8 minor. Now we have only 10 vertices. So among 10 vertices, most of them will be a single vertex here. Right, except 2, right? So except at most 2 vertices, 8 vertices will be a single vertex. Oh yeah, so if you pick 8 vertex here.
네.
What? if you pick 6 vertices, then 2 of them will be in the same bag, right? So out of that's right. No, what I was saying. So we are trying to prove that k8 minor doesn't exist. If I have a k8 minor, then at most 2 vertices of k8 are coming from 2 vertices, right? Think of the minor model. So that means 6 vertices from k8 was actually coming from a single vertex. Each of 6 vertices are from single vertex of k2. So if we pick 6 vertices from this graph, 2 of them must come from same bag. If they come from same bag, then they are non-adjacent. So that's contradiction to the fact that this was a minor, k8 minor. So this has no k8 minor. So this pattern that we see is true up to 7 doesn't continue. And instead, what we know is I forgot whose theorem it is. Number of edges is at most 6n minus 20 if G has no k8 minor. Now this is the first time that the pattern discontinues, right? So what can you expect in general? Now that has been a focus of study in 1980s. So now we have a precise answer. So the theorem due to Thomason 80s and Kostachka also 80s says that there is a constant universal constant C such that if a simple n vertex graph has no kt minor, then the number of edges is at most ct square root log t. Okay? Oh, times n. And this is also tight. I mean, what I mean is asymptotically tight. You can never improve. I mean, what I mean is that there is another constant c prime such that there exists a graph without kt minor and has c prime t square root log t n edges for many t's. And in Thomason even determined in 2001 that c is about 0.319 plus a little or 1. What that means is as t goes to infinity, c converges to this number. Okay. Now, may still hope that our fake bound still work for certain cases. So here's a conjecture by Simmer and Thomas, which says that if the graph is t minus 2 connected and large and no kt minor and simple, then number of edges is what you expect. By large, I mean the number of vertices is large, and this is known to be true for t is 8. This is Jorgensen's, and for t is 9. This is due to Jixia Song and Robin Thomas. And there is a similar theorem for topological minors. For topological minors, right, the question is, what are the maximum number of edges of graph without containing kt topological minor? And this is a theorem due to Bella-Bulobas. Oh. Robas and Thomason. And independently Kamlos Semeradi in 96. They proved that there is a constant C prime such that if a simple m vertex graph G has no kt topological minor, then number of edges is at most constant prime times t squared. And recently, maybe 5 years ago, Robin Thomas and Paul Wallan has a theorem which actually proved that this constant can be taken very small, like something like 20. Yeah. So if you take a 20, then you already get the good bound. All right, since we talked about the number of edges, now a natural corollary of all these things is that you can actually prove something on chromatic number. Okay. Right. So we proved that number of edges is bounded by constant times t times square root log of t times n. That means the average degree is also bounded. So no kt minor. Oh, no, I mean, we don't have, right, number of edges is constant t square root log t times n. So the twice number of edges divided by 2 divided by n, that's average degree, right? It's less than twice ct square root log t. And this is true for any minor of G, because if G has no kt minor, then every minor of G doesn't have kt minors. So that means every subgraph has a vertex of degree at most this. So that means chromatic number is bounded by ct twice c t squared log t. How far can we improve this? How far can you improve this? And so this Hardwig's conjecture in 1943 states the following. If a simple graph has no kt plus 1 minor, then its chromatic number is at most t. Oops. That's Hardwig's conjecture. So if you don't have a k2 minor, then you have no edges, so chromatic number is 1. If you don't have k3 minor, then you have no cycles, and then chromatic number is at most 2 because it's a forest. If you don't have no k4 minor, then it's a series paragraph. You can easily prove that there is a vertex of degree 2, and you delete it and apply induction and blah blah blah. So you can show that chromatic number is at most 3. If you don't have k5 minor, right, then chromatic number is at most 4. This is due to Wagner by using 4-color theorem. Why? Because, well, if Hardwig's conjecture is true for the case when t is 4, then it also implies that planar graphs are 4-colorable. So this is stronger than planar graph, stronger than the 4-color theorem of the planar graphs. But Wagner proved the other directions. If the 4-color theorem is true, then graphs without k5 minors are 4-colorable as well. And here's the theorem for the next case due to Robertson Seymour Thomas in 1903. They proved that minimal count example to the Hardwig's conjecture for t is 5 is an apex graph. What is apex graph? meaning which means that there is a vertex V such that G delete V is planar. So that's apex graphs. Right. So they proved that any minimal count example to the Hardwick's conjecture for t equal to 5, this is not at least, it's equal, is an apex graph. So you have a vertex of degree, vertex whose removal makes the graph planar. So if you have an apex graph, then I can remove single vertex, the remaining is full colorable, and then this single vertex, this vertex you give us the new color, then you only use 5 colors. If you use only 5 colors, then that's not a count example. So this implies that Hardwick's conjecture is true for t is equal to 6. No, 5, yeah. And now it's completely open for any values of t bigger than 5. Now, if you have such a theorem, how do we actually, I mean, no, this conjecture is still quite far, but very recently there's a big progress, and this is a theorem due to Luke Postel. (2020), and he proved the following. So graph has no kt minor, then it's ct log t to the 6 colorable. Previously we knew that ct square root log t, right? And this is big improvement because the square root log t become log t. But still we are very far, okay? All right, so that's it. Now we will move on to the next chapter. Oh, by the way, I didn't mention why we don't talk about the topological minor version for Hardwick's conjecture. It has been a conjecture actually, and which turns out to be false. So there are graphs which doesn't have KT topological minor and has large chromatic number. So I'm not going to mention that, but there are such graphs. All right. Now, the next topic is graph minors. I don't know whether the numbers are correct, but graph minors and well-quasi-ordering. Right, we already mentioned, I think I have mentioned it a couple of times, that the property of being, if some graph property is closed on the taking minors, there are only finitely many exceptions that you can characterize, that you can use to characterize this class of graphs. In other words, like planar graphs can be characterized by 2 forbidden minors. And there is a theorem saying that any property closed on the taking minors can be characterized by finite list of forbidden minors. So I will give some kind of introduction to this field, this theory. So to do that, we start with the well-quasi-ordering. Okay. So for a binary relation, we say Q this is a quasi-order if the following two axiom is true. If it is one, reflexive. What that means is x is less than or equal to x for all x in Q, and second thing is transitive. X is less than or equal to y is less than or equal to g implies that x is less than or equal to g for all x, y, z in Q. Okay, so this is a relaxation of a partial order. So partial order, for partial order you have one more relations. What is it? If x is less than or equal to y and y is less than or equal to x, then x is equal to y. Then it's a partial order. Now we will talk about quasi-order because graph minor is one example of quasi-order. We say, like for instance, example, h is less than or equal to g if h is isomorphic to a minor of g. Now this Q is a set of all graphs. Now this is a quasi-order because it's a reflexive. Graph is minor of itself, and it's transitive. If h is minor of g, g is minor of f, then h is minor of f. But this is not symmetric. If h is minor of g and g is minor of h, they're not equal, even though they are isomorphic, right? So because of this, you'd relax this symmetric condition and define quasi-order. But it's mostly like and we can think of it as something like this. So from partial order, when you take a quotient by the equivalence classes, then you get the from quasi-order, when you take a quotient by equivalence classes, then you get partial order. All right, now, oops. Now I will define a few terms. A quasi-order is well-founded if Q has no infinite strictly descending sequence x0, x1. So what is this notation? So when I say A is less than B in Q, that means A is less than or equal to B and B is not less than or equal to A. Okay, so that's strict inequality. All right. So let me give you examples, right? So for instance, if I take a set of integers and usual relations less than or equal, this is not well founded. Because you can continue forever, right? So 3, 2, 1, 0, minus 1, minus 2. There's an infinite sequence, strictly descending. But if I take the set of positive integers and this thing, then this is so well founded. And this is a set of graphs. Of course, here we talk about finite graphs. Then this is well founded. Right? Because when you go strictly down, right? So you start with some graph and you take a minor, which is right. So when you go to G1 to G2, then something must have been decreased, right? Number of vertices is decreased or number of edges is decreased. And this pattern cannot continue because number of vertices plus number of edges will be a non-negative integers. So it's well founded. And an anti-chain of a quasi-order is same as a quasi-order, same as anti-chain in the partial order, is a set of subset of Q such that x is not equal to not less than or equal to y for all xy, for all distinct xy in Q. Then it's anti-chain. Now I can define what a well-quasi-ordering is. This quasi-order is a well-quasi-ordering if it is well-founded and has no infinite antichain. Then we say something is a quasi-order. So let's see the example. No, well-quasi-order. So if I have a set of integers and these relations, then this is not a well-quasi-ordering. Why? Because it's not well founded. Right? It's not well founded. Okay, I mean I have two criteria. Is it well founded or no infinite antichain? It's not well founded. It doesn't have an infinite antichain because the size of maximum antichain is at most 3. Right? So, no, at most 2. No, at most 1. Right? You don't have antichain of size 2 because any 2 is compatible. Right? One is less than the other. So this is not a well-quasi-order. I mean, it has no infinite antichain. So one condition is satisfied, but the other condition is not satisfied. How about graphs? And we say H is less than or equal to G if H is isomorphic to a subgraph of G. Then this is well founded. This is okay, but the condition that there is no infinite antichain, this condition is not satisfied. How do we know? Well, you just take the cycles of different lengths, C3, C4, C5. No graph is a subgraph of another. So it's an infinite antichain. So it's not well-quasi-ordering. Right? So some quasi-order is well quasi-order, some quasi-order is not well quasi-order. So if Q this is a well quasi-ordering, then we say Q is well quasi-ordered by this. Now, I will tell you a few characterizations of well quasi-ordering. We need some property. So the goal is to illustrate you that graph minors is well quasi-ordering. Okay, before that, I will tell you some theorem. So let me start with something called infinite Ramsey theorem. 1930. So infinite Ramsey theorem is as follows: right? K be a positive integer for every coloring of edges of, okay, let K omega be the infinite, the complete infinite graph. On the countable infinite set. So if you're not sure what it is, so for instance something like set of natural numbers, right? Think of this. So K omega is, now this is the first time that we talk about infinite graphs. There are people who work on infinite graphs, and there's some of the theories are quite non-trivial there. So I don't normally work on infinite graphs, but here it is convenient to work on infinite version of graph to prove something on well quasi-ordering. So K omega, let's say K omega is the complete infinite graph. So you can think of it as a graph whose vertex set is set of positive integers, and any two are adjacent, and it's so that's why it's called complete. Now we say the following: for every coloring of edges of K omega by K colors, there exists an infinite complete subgraph whose edges are monochromatic. Right. So no matter how I sort of imagine that these are the vertices, 1, 2, 3, 4, 5, 6, 7, continues forever. So I have colors. So maybe this is blue. Let's say I'm using only 2 colors. I need to draw many. Maybe I drew too much. no matter how I color all the edges, I can always find some subgraph where every edge is the same color like this, or like the other color, right? So that's the statement. So how do we prove that? And proof is quite cute. It's a consequence of Pisano principle. So let's say these vertices are v1, v2, v3, v4, v5, v6, v7. Right? So we will keep taking a subsequence. So there exists a color CV1 that appears infinitely many times in V1, V2, V1, V3, V1, V4, etc. Right? All these edges, among all, so you have infinitely many edges, but number of colors is finite. So among these infinite many edges, one of the colors appear infinitely many times. So that's the color CV1. Now, by taking a subsequence, we may assume that color of, okay, let's see the V1 color of V1, V2, the color of V1, V3, color of V1, V4. All these things are equal to CV1. Right. So right, what I mean is I pick V1, pick V1, and then let's say if it's red, then I only look at the neighbors which are adjacent by red edges, and for others I delete it. I still have infinitely many vertices, so I don't lose anything. Right? This is the beauty of the infinite graphs. Right? Even if I delete something, I may still have a graph which is still infinite. Now, what's next? Similarly, okay, let me say for each I, take CVI as the color that appears as a color, because you might have many colors that appears infinitely many times. In Vi, Vj, for j bigger than I. Then we, by taking subsequence, we may assume that Vi, Vj for all I less than j as the color CVI, right? So starting from 2, right? So we look at V2, V3, V2, V4, V2, V5, etc. And among all these colors, all these edges, one color appear at least one color appear infinitely many times. So I'm gonna remove all the vertices that is not connected by this edge, this color. Then what's left is again some infinite sequence, and then I do for 3, right? So take a CV3 as the color appearing infinitely many times in V3, V4, V3, V5, etc. And then take a subsequence, and then I look for V4, right? Take a color that appears infinitely many times, and then take a subsequence, and then V5, and then take a subsequence, and then V6, and take a subsequence, and then continue forever. Then we have some subsequence. So this gives an infinite sequence V1, V2, such that the color of the edge Vi, Vj is equal to CVi. Now, still this graph is not monochromatic, but by the Peason's principle, this again has an infinite subsequence W1, W2 of V1, V2 such that CW1 and CW2, all these numbers are same. Now that gives me the, right? So W1, W2, this induces a monochromatic complete infinite subgraph. Okay, so that's the proof of infinite Ramsey theorem. Now, why did I talk about that? There's a very nice corollary for quasi-orders. So this is a theorem. Okay, so let Q this be a quasi-order. Then the following are equivalent. So one is Q this is a well-quasi-order. Second thing is every infinite sequence A1, A2 of Q has a pair IJ, AI, AJ with I less than J such that AI is less than or equal to AJ. That's the second property. And the third property is infinite sequence A1, A2 of Q has an infinite subsequence. AI1, AI2, AI3, for I1 less than I2, less than I3, etc. such that AI1 is minor of AI2, which is less than or equal to AI3, etc. Alright? So this is one of the key property of the well-quasi-ordering. The proof is quite nice. So this 3 implies 2, that's easy, right? Because if you have an infinite subsequence, then you have just take AI1 and AI2, then you get 2. And 2 implies 1, that's easy, because we need to prove that it's well-founded and has no infinite antichain. Right? If it's well-founded, then you have a strictly descending subsequence, and that contradicts 2. If you have infinite antichain, then you can take an infinite sequence from elements in the antichain, then that also contradicts 2. So this direction is trivial. What's left is 1 implies 3. And there we use infinite Ramsey, right? So let A1, A2 be an infinite sequence of Q, elements of Q. Now we color edges of K omega as follows. So C V1, Vi, Vj is 1, 2, 3. So you have 3 colors. So when is it 1? If Ai is less than or equal to Aj, then it's 1. Okay. 2, if Ai is not less than or equal to Aj, but Aj is less than or equal to Ai. Oh, so what that means is Aj is strictly less than or equal to Ai. And 3, none of the above. So Ai is not less than or equal to Aj, and Aj is not less than or equal to Ai. So we have 3 colors. So given an infinite sequence of elements from Q, we have 3 coloring of edges of the complete infinite graph, and we apply Ramsey by the infinite Ramsey theorem. There is an infinite subsequence. Infinite subsequence AI1, AI2, AI3, etc. where I don't know where I1 is less than I2, and the color is same for all I less than j, right? Color of Vij. Okay, I shouldn't have chosen I, but anyway, that's it. So what's happening? If the color is 3, then Q has an infinite antichain. That's contradiction to the fact that this Q is a well-quasi-ordering. If color is 2, then this so infinite antichain is this. If the color is 2, then Q is not well-founded, because AI1 is bigger than AI2, is bigger than AI3, etc. Right? So the color has to be 1. That means AI1, AI2. Right? So that's it. And this is a very useful tool to prove whatever theorems on well-quasi-ordering. Right? So in the next lecture, I will give you some more examples about well-quasi-ordered sets and build enough tools to prove Kruskal theorem. Right.